All right, guys, welcome to the next installment of Great Start. Next installment of me trying to teach you from my house. Now, we're going to be looking at populations, which is a good tangent right off of ecology, and it's going to study groups of um, different species in an area. So, we're going to be looking at and this is going to be over 2 videos, but we're going to look at the cockroaches, we're going to look at penguins, we're going to look at kangaroos, we're going to look at a lot of different organisms. Now, first, when populations enter a new area, you're going to see that they're going to go through exponential growth. Exponential growth is also known as a J curve because you could see that 2 become 4, 4 become 8, 8 become 64, and it grows really fast, really quickly. This population shoots right up. The thing is, exponential growth only occurs if there are no environmental restrictions. So there's unlimited space, there's unlimited food, there's no changes in weather or climate. Everything is ideal for them. And at first, we could see that they entered a new area. And actually, with the invasive species, this is perfect because you can see they enter a new area and there's no predators. They do have nearly unlimited space. They have tons of food because they're entering a new food web and they have a completely new niche and they just kind of take off. But even with exponential growth, at some point they're going to start to feel those environmental restrictions. And as a result, the population is going to start to drop off. Instead, what we see is the population goes through that initial exponential growth phase, but it starts to drop off and then stabilize. The point at which it stabilizes is called the carrying capacity. And this is going to be the limit that the population can safely be at in an area. So this is going to be, all right, based on the amount of food provided, the space provided, the competitions, the predators, everything, this is how many can live in a certain area. If you go above that number, well, you're going to see that you're going to get a higher mortality rate. More things will die. If you go below that, well, suddenly there's an abundance of food, there's an abundance of space, and the birth rate's going to go up until it reaches that carrying capacity. What we see is those populations are always going to teeter right around that carrying capacity. So the things that can limit the growth or restrict the growth are going to be the other piece of this. Really, the big takeaways here are exponential growth occurs under the most ideal circumstances. It can happen, but it's not sustained because once you start to get environmental restrictions, there's going to be a higher mortality rate. And when we see mortality, you're going to kind of teeter off into a carrying capacity. So, exponential growth, this is called the J curve, and logistic growth is called instead more of an S curve. So, limiting factors. What are limiting factors? These are the things that in an environment can restrict the population from going to infinity. And there's really two types. The first is density dependent limiting factors. And these have a proportional intensity to density. What does that mean? Well, the more densely packed a population is, they tend to have a much stronger effect than if the population weren't densely packed. With density independent limiting factors, these are things that are going to kill things off, whether there's 1 or 1 million in an area. It's non discriminatory. These are going to just wipe things out. We'll look at two populations. On the left, we have a very low density population of penguins. So low, in fact, that you can see literally just one in this entire area. Whereas on the right, we have a very high density of populations, or a high density population. Ton of penguins in one area. This is a dense population on the right. This is a low density population on the left. Think like, I don't even know of any towns in North Dakota, but pick a random town in North Dakota. For humans, this is what it would be like versus New York City. Now we see that all of these in the middle are going to be limiting factors. They're going to limit a population from growing to infinity in some way, shape, or form. However, some tend to be a lot worse in this scenario on the right than in this scenario on the left. First one being disease. Now you can see disease, especially now with our COVID-19 pandemic, is going to be taking off in these very dense cities. Now, Connecticut has kind of been the byproduct of New York City, but if you look at New York City, its growth there has been insane. Actually, I was just looking at the numbers right now, and I think there were 3 or 4 confirmed deaths in North Dakota. There's like 13,000 in New York City. Now, of course, that's because there's more people there, but if you think about disease, the way that disease spreads is through these interactions. If this penguin were to get sick, and it interacts with everybody over the course of 3 days that's around them, it's not really going to spread to many. Sure, maybe this one penguin would die off from that illness, but it's going to be fairly remote. Now, if, say, this penguin right here were to get an illness, and it has a disease, it's going to be able to spread to all of these very quickly. Because of that, a disease would be what we would call a density-dependent limiting factor. It's worse in this scenario than in this one. Now, food scarcity. Let's say that there's a food scarcity here. This penguin has less food available. Well, it still has a huge area that it could go to find food, and as a result, it's probably going to be able to get a meal. Whereas here, if there's a food scarcity, you have a couple options. Either organism A gets it and B starves, organism B gets it and A starves, or A and B both get a little bit of food and they both kind of suffer malnutrition but survive. Now, if you were to think about a food scarcity in this area, there's most certainly going to be a lot of death because there's just so many organisms in that area. Now, this plays itself really well to competition for land, competition for other resources like water, mating, things like that. We tend to see that when you have higher competition, this population on the right is going to suffer more as a result. And then finally, with predators. Let's say there was a polar bear right here. This polar bear were to come up, eat this penguin, it has no chance. The penguin's dead. Tragic story, but really it's a drop in the bucket because if a polar bear were to be right here, and go after this population, the amount of damage it's going to cause to this dense population is going to be significantly larger. So these first 4 are all density dependent limiting factors. The denser the population is, the more they're going to restrict its growth, more deaths. Now, something like human impact, this would be, humans decide to build a mall right here. This penguin has to leave. It may die. Humans decide to build a mall right here. These penguins have to leave. They may die. Now, regardless, you're going to see that human impact can kill them non-discriminatory. It's going to kill all the penguins in the area, or they all have to move and they all have to figure out something new. So human impact doesn't discriminate, and as a result, it would be a density-independent limiting factor. It's going to limit the population's growth regardless of its density. Another one is climate. Let's say we had a drought or it had gotten really hot in an area. Let's say that the net temperature in this area went up 20 degrees. Well, this penguin has no chance, and as a result, it's going to die. If this area's temperature went up 20 degrees, well, these penguins have no chance, and they too are going to die. Now, we're going to see that you have a high mortality rate here. But realistically, we're going to see that all of these die and all of these die. And as a result, that would be a density-independent limiting factor. The third is a natural disaster. If a volcano were to emerge through the ice right here, it's going to undoubtedly kill this penguin. If a volcano emerged from the mud or whatever they're dancing around on right here, it's undoubtedly going to kill all of these penguins. Now, if it's going to kill all of them regardless, and they're all affected regardless of density, this guy is affected or all of these are affected, that too would be a density-independent limiting factor. And I believe that is it. So that's going to be my first video. I already recorded this once, but it was too long. So now I'm going to break it up into pieces. That's going to be it for today. Those are your growth curves and your limiting factors. See you soon, guys.